Hi everyone, today we're covering 2.7, VSEPR and bond hybridization. We'll talk first about geometry or VSEPR. VSEPR is valence, shell, electron, pair, repulsion, and it's just the method we use for determining geometry. We basically have the one rule, which is to get atoms, and especially lone pairs, as far away from each other as possible. That's really our one goal when we're trying to figure out the geometry of a molecule. And so what I'm going to run through now is all the different possibilities of what we can have based on the total number of bonds that are happening in our molecule. So in order to do this, I'm going to take it from a lone pair perspective. Right, we want to balance. We want to get these geometries so that the lone pairs are as far away from each other as physically possible. And so we're going to think of every possible number of lone pairs that a central atom can have. And so I'm going to make a table here. I'm going to have number of outside atoms. I'm going to have 0 lone pairs. I'm going to label that LP. 0 LP, 1 lone pair, 2 lone pair, 3 lone pair, and 4 lone pair. So these are all the different combinations we can have. For outside atoms, we can either have 2 outside atoms, 3 outside atoms, 4, 5 in the case of expanding an octet, and then finally 6. And so this is all of our possible combinations that we can have to have all of our molecular geometries. So let's say I have 2 outside atoms and 0 lone pairs. I'm going to call my inner atom M, and anything on the outside I will call X. In order to get these as far away from each other as possible, it has to be linear, and it has to have 180 degrees of that bond angle. In the case of 2 atoms on the outside, there's no possible way that I can have any lone pairs in that center atom. And so if I have 2 outside atoms from my center atom and 0 lone pairs, it is going to be linear by definition. Now let's say I have 3 and no lone pairs. Again, I want to get all my X's as far away from each other as possible, all my outside atoms as far away from each other as possible. And if I do that, I'll end up with what's known as a trigonal planar structure. And this bond angle is 120 degrees because that's as far away from each other as they can get. Now if I have 1 lone pair, it'll look a little bit like this. And I'm going to, for the purpose of this kind of discussion, I'm going to assume that a lone pair is like a bond. Again, the angle here will be 120 degrees between those 2 atoms, but because this lone pair doesn't actually show up, our geometry is bent. You can see it looks linear, but it's just kind of bent a little bit, so we just call it bent. Now, if you have 3 outside atoms, there is no way you can have 2, 3, or 4 lone pairs in that central atom and still satisfy the octet rule. For 4, we'll have our simplest case, which is no lone pairs, M in the middle, X here, X there, and then we'll have 2 more, one that's coming out at us, and the other one that is behind the page, which I'm going to just use that hash line to do that. We call this tetrahedral, and the bond angles are 108 degrees, which is as far away from each other as they can possibly be. We'll replace one of those, we'll just do this top one, for example, with a lone pair, and the other ones still end up in the same spot, but remember, that lone pair doesn't actually exist. It's just how we write down the electrons. Here, we actually call this, if we look, it's a pyramid with three sides on the bottom. We call this a trigonal pyramid. Pyramid. Now let's replace the second one with a lone pair. We have M in the middle. We have 1 lone pair here and 1 lone pair here. X is in the back and X in the front. From this, we have another bent shape because it looks very similar to the bent one from before. And this angle here is about 108 degrees. And so you notice the distance between all of my atoms on the outside stays the same, despite the fact that the name of the geometry changes a little bit. And again, I can't have 3 lone pairs or 4 lone pairs in the case of 4 atoms on the outside. I'm running out of space here, so I'll move 5 and 6 down a little bit. But after this, we have 5 outside atoms. Again, we'll have our simplest case, which is M in the middle. We have one X up here, one X to the side, another X to this side, and then we have one X kind of in the back of the page and another one in the front. Of course, all of these are 3-dimensional, and so the hash line is just saying it's going back from the plane of the board or the page, and the X and the little wedge is coming towards us. I can't actually show you this in 3D though, so that's why we use this simple notation. For here, things get a little more complicated. These straight lines have about a 90-degree angle, whereas the bent ones are 120 degrees from each other. And this is the only way that we can actually depict this and get this the most stable and have everything as far away from each other as possible. If I have one lone pair, what I'm going to do is I'm going to put that lone pair going up top, because that is as far away from everything else as possible. And what we call this is a seesaw, because it looks a little bit like a seesaw. Again, the angles here between the wedge and the straight is 90 degrees, and between the wedge and the dash is 120 degrees. We can go to 2 lone pairs. For this one, we'll have M in the middle. We'll have X up top, X on the side, and X on the other side. And because we have 2 lone pairs now, those end up on the wedge and dash, because that's as far away from each other as possible, whereas these are all 90 degrees. We call this a T-shape. That's in the case of 2 lone pairs. If we have, and I'm going to just rewrite this down here so it's easier to see, because this table is getting a bit large. For the case of 5 outside atoms, we can also have 3 lone pairs, and that one generally looks like this. We'll have M in the middle, X on each side, and then the lone pairs end up on this, on the front and back, as well as the top. And this is a linear molecule, because the X's are completely far apart from each other, and all of these lone pairs are 120 degrees apart from each other. Okay, the last one we can have, and this one, of course, is the most complicated because we have a lot of bonds, is 6 outside atoms. If we have 0 lone pairs, this is what the molecule would look like. We'd have 2 facing the back of the page, 2 coming towards us, 2 up and down, and the angle between each of these is perfectly 90 degrees. So you have 1 coming right at you, 1 going right behind, and then we have 2 towards the sides, and then 2 up and down with 90 degrees between each of them. That's 0 lone pairs. If we have 1 lone pair, we end up with what's called, and this is called octahedral. For 1 lone pair, we end up just substituting one of them with a lone pair. Otherwise, it looks exactly the same as before. And this is a square pyramid. And for all of these, you'll notice that the distance is always 90 degrees because you can't really get any closer or further away than 90 degrees here. For 2 lone pair, we put them at the opposite ends. So, we put the lone pairs at the opposite ends because that's as far away from each other as possible. And then the X's occupy the kind of ring in the middle. We call this square planar because it's a square and it's all in one plane. We have 3 lone pairs, and for that we'll have M in the middle, and we'll have the lone pairs sort of like this, because again, that is pretty much as far away apart as you can get. Everything is the same distance, so I can't really get any further than this. We call this a T-shape. Again, 90 degrees between everything. And finally, for 4 lone pairs, we end up with a linear molecule where I have X's on opposite sides and my lone pairs all around the middle like this. And this is a linear molecule. And so, of course, when you get down to these geometries, it gets very complicated, but what I'm trying to emulate to you is that based on the number of lone pairs, you're going to want to get them as far away from each other as possible. So anytime you're drawing your Lewis structure, you don't necessarily have to commit this to memory because this is not really possible to commit to memory. You want to draw your structure and just make sure that your lone pairs are as far apart as possible. For example, let's say I have something like this right here, right? This T-shape. I would not necessarily draw this structure. Because these lone pairs are 90 degrees from each other. They're way too close. I would rather have my lone pair here where it's further away. And so that's essentially what you want to think about. And you want to draw your Lewis structure like this and then just look at the geometry and make a guess. And so here, right, if I look at this one here, it's kind of bent, right? It isn't trigonal planar necessarily. It's a little bit bent. And so from there, I can tell that it's a bent molecule. It's a little bit tough, but the biggest thing that I want you to get from this is to look at this structure and just make sure that your lone pairs are as far away from each other as possible. That was a lot, but the second topic we're going to talk about is hybridization, which is essentially what do your orbitals look like once you have these different molecular geometries. So anytime we're doing VSEPR theory, we always want orbital overlap. That's how bonds are made. It's by overlapping their orbitals. So in valence bond theory, electrons of two atoms begin to occupy the same space. We call this orbital overlap. We've looked at this before, but for good bonding to happen, they can't be too close. They can't be way too far away. They have to be just in this little Goldilocks zone where there's enough overlap, but the nuclei aren't too close to each other. And so what atoms end up doing, or what molecules end up doing, is they start hybridizing their orbitals, or instead of having orbitals all in different energy levels like this, they essentially mix them together. And so what'll happen is you see this 2s and 2p here get mixed into what's known as an sp orbital. And the reason for doing that is that it lowers the energy of these orbitals, and so you don't have as much high energy orbitals anymore. This process is called hybridization. So the simplest form of this is an sp orbital, where an s and a p orbital mix together to yield two new orbitals that are the same energy. So I have one s, I have one p, and I have this new sp orbital, which has this little tiny lobe back here, and a larger one, and again a larger lobe, and a tiny one. And together, they look like that. Whenever I have sp orbitals, these specifically align themselves in a 180 degree fashion. And so if I have a linear molecule, its orbitals must be sp, because sp can only overlap in 180 degrees. The next is sp2, where one s orbital will mix with two p orbitals. Again, these look sort of similar. It's one big lobe and one small lobe, but then drawn together, they make this triangular shape. They are 120 degrees apart from each other, and you might see where I'm going with this. This is a trigonal planar molecule. And so if I have a molecule that's trigonal planar, it must have only sp2 orbitals. Finally, sp3, I mix one s orbital with three p orbitals. I end up with those lobes, and they're all in a tetrahedral shape, where at each of these poles, they are 109.5 degrees away from each other. And so this will result in a tetrahedral geometry. And so if I have something that's tetrahedral, it must be sp3 hybridized. This is just taking a look at that together. If I mix s and p together, I'll end up with two new orbitals that are sp. It has a linear geometry. If I mix one s and two p, I end up with three new orbitals that are sp2, and those are 120 degrees apart in trigonal planar. And then sp3, I'll mix one s and three p. I should get four new orbitals that are sp3, and it's tetrahedral. Now, based on that, we can get multiple different types of bonds, particularly double and triple bonds. So single bonds come from sp orbitals. Any of them, sp, sp2, or sp3. Double or triple can only come from p orbitals. And so when you're drawing a molecule, and you'll see this in the next few slides, we can have different kinds of bonding based on whether or not it has sp or p orbitals. If we have a single bond, we call that a sigma bond, and a double or triple, we call a pi bond, and these overlap sideways. So sigma bonds will overlap basically head to head. And so if we have our p orbitals overlapping, they'll overlap like this, where they essentially the bigger parts collide into each other. Or if you have an S and a P overlap, they collide exactly like that. And so you end up with a single bond from doing a sigma overlap like this. Pi bonds, on the other hand, are sideways overlap. And so you see here I have my sigma bond, my single bond between C and C. My p orbitals kind of stick up, and then these will mix together. Those will overlap, and I'll end up with this big cloud of electron density at the top and bottom. And those are what we call the pi bonds. And so let's look at a molecule of N2. If I draw the structure of N2, I'll do this. Each N has 5 electrons, and so at the end we should have 10 electrons. If I make one bond, that's -2. I end up with 8 electrons. I can put a bunch of lone pairs on it, but in reality what happens is I just form multiple bonds, and then I put my lone pairs. And so this is the Lewis structure for N2. If I think about this in terms of sigma and pi bonds, this is what the orbitals actually look like. On N, I have one big sp orbital. On the other end, and I have another sp orbital. And there, I have 2 electrons being shared. That's my sigma bond. Now on the side, I have one p orbital there that has a top part and a bottom part. And I have another p orbital here that also has a top part and a bottom part. These two will share electrons in a cloud above the nitrogen. That's my pi bond, and that's just one of them. On top of that, I have another set of pi bonds that are doing the exact same thing, where these two are essentially sharing electrons, and that's my second pi bond. Now this is just a more complicated version of showing this right here. The point that I'm trying to get to you is that a single bond equals a sigma, and then double / triple equal pi bonds. Now the last important thing to remember here with multiple bonds is that if you have more than one bond, they're stronger and shorter. Pi bonds pull the atoms closer together because you have this big cloud of electrons above your molecule that's pulling it closer together. And so anytime you have these increasing bond orders, you get stronger and stronger bonds. That's all for this video. It was a lot, and so I'm happy to answer any questions, but for now that's all. Thanks, guys.